In this example, we're going to be looking at the stresses in the beam due to the bending and shearing. So we'll have a look at a simply supported beam as shown here. This beam will have a T section, and to begin with we'll need to be able to get the shear force and the bending moment diagram as shown there. So I'm going to presume we are able to firstly get the reactions and then plot the shear force diagram and the bending moment diagram as I've got it here. The bending moment, it will follow the convention that sagging is positive and it's plotted positive down. Okay, so the first thing we're going to do is actually to work out the second moment of area of what is a T section for this beam, and we will need this second moment of area before we can actually find the bending stress and the shearing stress. So second moment of area for this T beam, which we will presume to be made out of two blocks of material. Firstly we have the flange and then we have the web, and they have their individual dimensions as shown here. To get the second moment of area, we need to firstly find the centroidal axis of this overall section. It's not too difficult to find the centroid of the individual blocks, and they are just halfway up the rectangular blocks, but what we actually need is the centroidal axis for the overall cross section, and for that we're going to take moments. I'm going to take moments about the top edge. It could be about any edge, but the top is just a convenient place. So first moment, taking first moment is area times the distance to the centroid. So I will firstly do it for the individual blocks, and then the sum of the moments for the individual block has got to equal the sum of the moment for the total section. So let's just take the yellow block firstly, and it as an individual block. So the area of that block is 150 times 20, that's the area, and the distance to the centroid from the top edge, seeing the block has thickness 20, or from the top edge to the centroid, that has a distance of 10. So that's how much moment there is due to the yellow block. Okay. Secondly, for the blue block, the area is 280 times 15, and then again the distance from the top edge to the centroid of the block. There's the centroid of the block, it's halfway in there, so from there to there that's 140, and then we have to go another 20. So the distance from the top to the centroid is actually 160 millimeters. So that is the first moment due to the blue block about the top edge. That is, when we add the two together, that is the sum of the moments of the two blocks taken separately. Now that's got to equal to the first moment of the whole area taken as a combined section. So the total area there, the total area, so that's got to equal the total area, which is 150 times 20 plus 280 times 15. So that's the total area of the overall, and that area is multiplied by the distance to the centroid of the total area. So that is how we find the centroid of this combined area, and that gives us a y bar value of 97.5 millimeters. So that is necessary because the beam is going to bend about the centroidal axis or the neutral axis of this section. So if we're going to find the second moment of area of this T-beam, it will be about its own neutral axis, about its own bending axis. For that, we're just going to use parallel axis theorem, as well as the second moment of area of the individual blocks making up this T-beam. So the second moment of area, I, for a rectangular block, of which these are so rectangular blocks, so B times the breadth and depth. If you have a rectangular block of breadth B, depth D, then the second moment of area is equal to BD cubed over 12. And that would be for each of these blocks bending about their own individual centroids. But we're now making them bend about the neutral axis of the overall section, so that will increase the second moment of area. By the use of the parallel axis theorem, you will get the I of the new, as you move the block, you will get a new position, and the I value will be then equal to the where you were, plus the parallel axis bit, which is AV square, where A is the area of the block and V is the distance between the two centroids. So let's do that by example for both the yellow and the blue blocks, and then this will become clear. So firstly, we're working with the yellow block, so I of the yellow block using BD cubed over 12, well, that yellow block has got a breadth of 150, the depth is 20, so BD cubed over 12 is like that. That would be for bending about its own centroid, but we're making it bend about the neutral axis, so we've got to add the AV square bit. A is the area of the block, which is 150 times 20, and V is the distance from the block's own centroid to where we are now making it bend, so it's that gap there. Well, Y bar is 97.5, and that is 10, so this gap from the centroid to the neutral axis must be 87.5. So that's 87.5, and it's squared. Quite easy to forget the square bit, so I do take note. So that is the I value now for the yellow block bending about the beam's neutral axis, and but that's just for the yellow block. So we also need the equivalent for the blue block. So BD cubed over 12, the breadth is 15 there, the depth is now a big 280, 280 raised to the power 3, BD cubed over 12. So just notice when you turn the block around and you've got the much greater depth, how that has a much increased effect on your I value. I value always comes with the depth of the beam. Now that's the I value of the blue block bending about its own neutral axis, but we're making it bend about the centroidal axis of the beam, so we've got the AV square component. A is 200 times 15. V, is the distance from the block's centroid to the neutral axis of the beam. So we're talking about this distance here, and that distance there, well, we can work it out. The overall depth is, sorry, from here to here is, let's write it out, from here to here, that is 140, and what we're looking for is this particular gap. Okay, so overall depth is 300 minus 97.5 minus 40, so it is actually 160 minus 97.5, and it is squared. Okay. So this is the second moment of area for the blue block bending about the neutral axis. So the second moment of area for the whole beam is actually all of that added together, which actually comes to 66.9 times 10 to the 6, and it's millimeter to the 4 for all of these dimensions being in millimeter. Right, that is the second moment area of the whole I-beam. Okay, this is the I-beam with its loading, and we've got the second moment of area now found, and we're going to firstly look at the bending distribution. So for the bending moment, we get from the bending moment diagram, the bending stress comes from the bending moment using the engineer's bending equation, that which we call the Misy equation. M over I is equal to sigma over y, where sigma is the stress that we get for any distance y away from the neutral axis of the beam. So if we want to get the distribution for the stress at any particular position in the beam, we firstly find out for that position what is the bending moment that goes in there. I is this second moment area, and then the stress will vary up and down the beam depending on what we put into y. Typically we want the largest bending moment, a bending stress, so we will get that from the position of the beam with the largest bending moment, which in this case is 24. I'm working to units of kilonewtons and millimeters, so this will be 24 times 10 to the 6 if I change it to newtons and millimeters, because that's 24 kilonewton meter. So M will be 24 times 10 to the 6. I is 66.9 times 10 to the 6 millimeter to the 4, so consistent with the millimeters there. Stress is what we want, and then y is what we put in. Now that distance to the neutral axis is 97.5, so there clearly is a much bigger distance to go downward than upward from the neutral axis, and if we go down we actually can go 202.5 millimeter. So the largest stress is going to be at the bottom of the beam rather than the top. So if we put 202.5 as our y, then we will get stress max there is equal to 72.7 newtons per millimeter square. So if we just plot the bending stress like that, we would have, so the stress here is 72.7. It will be at the bottom of the beam, at the bottom of a sagging point in the beam. So if your beam is doing that for sagging, then at the bottom of it, that will be in tension because you're stretching the material there. So this will be a tensile stress. So this will be a distribution of the bending stress sigma, and all below below the beam, below the neutral axis, it is in tension at location C in the beam. So to get the largest compressive stress, the compressive stress at the top here, and the largest value of compressive stress, but all we need to do is same bending moment, same I value, but change the Y value to now go up to 97.5, so 97.5 in there, and it will get a stress value of 34, well, it's actually 35.0, rounded up a bit, 35.0, and it will be compressive. Okay, so that's the bending stress distribution, and we obtain the bending stress distribution from the Misy equation. The other thing we can get is the shear stress. So shear stress comes from the shear force, and the equation we use there is what we call the FaybI equation, F A y bar over bi, where b is the length of the how much we cut. Incidentally, that b is not the same as the bd cube over 12b. Okay? They're both in the same direction, but they have a slightly different meaning. So I'll say more about this b as we come to it. Now, the one thing that you will have to know is that when we're talking about the shear stress distribution, it is very unlike the bending stress distribution. So if we plot the shear stress tau, it is very unlike the bending stress in that the shear stress is max at the neutral axis. So the shear stress is maximum at the neutral axis level, whereas the bending stress is actually 0 at the neutral axis. So the shear stress is the maximum where the bending stress is 0, and the shear stresses, well, in this case you see that their shear stress is 0 top and bottom, and the bending stress are actually at their maximum values top and bottom. So the distribution of shear stress is very different to the distribution of the bending stress. But I have just said that the shear stress is maximum at the neutral axis, so this is the value of the shear stress that I want to find. Now, to find the shear stress, what we do is we go to our beam and we make a cut in the beam. And since I want to have the shear stress at the neutral axis level, I make a fictitious cut in the beam at the neutral axis level. So how much distance I cut through in the material, that is my B value, it's the length of the cut. Okay. Having made that cut, I have now got two areas that I've isolated. I am going to choose the area underneath. I could choose the area above, but it looks a little bit more complicated because the area above has two bits to it, whereas the area underneath is only a straightforward rectangle. Right, that is the area that I've isolated. So this A is the area of that bit there that I've isolated. Well, actually, let's put some values into this as we go along. Okay, let's see. So B was the length of the cut. So in the original problem, we see B, the web there has a thickness of 15, so B is actually 15. Okay. A is the area of that shaded blue bit there, so A is 202.5 times 15. So that's the size of the area. Y bar, well, Y bar is in the shear stress equation is actually the distance from the neutral axis to the centroid of the area that I have made a cut and expose. So the area that I'm talking about is this blue shaded area, so there is that centroid. So Y bar is the distance from the neutral axis to that centroid. So it's actually in this case half of 202.5. So it is actually 202.5 divided by 2. Okay, so that goes there. I don't have the space to insert it, but that's what it is. F is the shear force. From the shear force diagram, since we want the largest stress, we also need to have the largest shear force. So we look through the shear force diagram to look for the biggest value, and the biggest value is 31 times 10 to the 3 newtons, which is this value here. So that's the largest shear force in the beam is 31 kilonewton, so 31 times 10 to the 3. Now that leaves us with I, which is for the overall cross section. Sometimes people mistake I for the second moment area of this area. No, it's not. I here is the second moment area of the overall cross section, which we have discovered a bit earlier as 66.9 times 10 to the 6 millimeters to the 4. So these are then all the values we require for finding the shear stress at this point, and when we do the calculation, we get actually a shear stress value of about 9.5 newtons per millimeter square. So the maximum shear stress is significantly smaller than the maximum bending stress, as is typically the case for a fairly long beam with not much depth in it. The beam is generally, typical beams generally have bending as the dominant action. So that gives us the shear stress value at the neutral axis. I will just sketch out the picture of the shear stress distribution. If I just can line it up a bit. So there's the top of the flange, that's the bottom of the flange, there's the bottom of the web across. So the shear stress would start 0 at the top. It would go, actually a quadratic shape, this, so parabolic, and then there will be a jump onto the web, and then it will increase to a maximum and then decrease to 0 at the bottom. So the shear stress distribution would look like that. And if we wanted to get the separate values, since it's not a straight line, we will have to go at various points at various levels to make a cut. So if we wanted the shear stress at this level, we would then have to make a cut here, go back to the FaybI equation to get the values. So as you can see, the shear stress value is not so easy to obtain as the bending, because with the bending you just simply go to find the two maximums and you join it up with a straight line, and you know that the bending stress distribution is like that. But because the shear stress is parabolic, it's less easy to find, and because also the shear stress typically is not as big and therefore important as the bending stress, we are less reluctant to go and do the hard work to find out the value, and we actually fairly often just go for an approximate. So it is approximate, and we simply go for the average shear stress, knowing that it is not the actual correct value, but it's fairly good. So I'll show you what the average shear is. So the average shear is, we take the shear force and we divide it by the area of the web. Okay? So in here, the average shear force, the shear force was 31 kilonewtons, or 31,000 newton. The area of the web, 280 times 15. And if you do this calculation, we actually get a stress value of 7.4 newtons per millimeter square, okay, which is not very different to the 9.5. And so for practical work, we actually fairly often just go for what we call the average shear, because that's not going to be very different to the maximum, and if we have a beam where the depth is quite small, and the beam is quite long, and the normal loading, this is good enough a figure to work by. Okay, let me just finish off with one further thing, which is that, notice when I made the cut for the shear stress, and I've got two areas. Once I've made the cut, I then have two areas. I've got the area above, so it's that one there, and I've got the area below, which is the one there. And I've gone, when I was doing the AY bar up here, AY bar up here, I went for the blue area, simply because the blue area is a bit easier to calculate than the purple area. But just to show you, AY bar, so AY bar in the blue, that was 202.5 times, that is 15, so times 15, that's the area. The Y bar is distance to from neutral axis to the centroid, that was 202.5 over 2, so that's the Y bar. So this is AY bar in blue. Now if we did the AY bar in the purple, then we should get exactly the same answer, but it is a little bit more involved because there are now two blocks to it. I'll call that the top is 1, and I'll call this number 2. So let's do the AY bar of the top block, so it's got the centroid there and the centroid there. Area of the top block is the 150 times 20. That is the size of the flange, so you can just have a quick look at the 150 times 20 was the size of the flange. Okay, so 150 times 20, and then the Y bar is from the centroid here, so neutral axis here to the centroid, so we're talking about from here to here. Well, that's 97.5 minus 10. That bit is 10, so this is what we want. 97.5 minus 10. 97.5 minus 10. Okay, so that is for the first bit, and then we add on the second bit, which is this block here. So width 15, so it's 15 times, and that distance there, well, if that's 97.5 and this is 20, then this must be 77.5. That's the area of this block, and the distance from the neutral axis to this centroid must be 77.5 over 2, and this bit then is the AY bar of area 2. And what I'm saying is, when you add both of these up, you get the AY bar for the pink block, and in both of these, if you calculate it, both of these actually equal 307,550, and it's millimeter to the 3. So the point I'm making is, when you've made the cut, doesn't matter where you've got two areas, above or below, it doesn't matter which way you look, you get the same AY bar. So obviously, because it doesn't matter which way you look, you go for the simpler calculation. Okay, that then is an example of a beam with some loading, they're giving us shear force and bending moment, and then from the shear force we get the shear stress, and from the bending moment we get the bending stress.